Basic Econometrics.
The first statistical test for the linear regression model that I want to look at is called a two-sided t-test. And it is good for testing null hypotheses of the form H. Also for the null hypothesis, we often put H0. The true coefficient of x1 is equal to some number beta 1 not, and this is just some number that we make up. For example, previously I put this equal to 5. So the way that the idea of the test is as follows. So we take this hypothesis very seriously and we say, let's go ahead and pretend that it is actually true. And then let's think through the implications of this assumption. So if this assumption is met, in addition to our usual OLS assumptions, then we know that beta 1 hat, the OLS estimator, has a normal distribution that is centered at the true value. And in our pretend reality, the true value is, for example, 5. Now, a property of the normal distribution is that we cannot rule out any number. So a normal distribution can realize to any number, but numbers that are far from the center of the distribution are very unlikely. So a large distance between the estimator beta 1 hat and the center of the distribution is possible, but very unlikely. So now what we do once we have, we draw data, obviously. And now we have our sample and we can actually compute this distance. So we look at distance between our estimate and the hypothesized center of the distribution. And if that is too large, and we'll be more precise about what too large means in a second. But if this is too large, then something that shouldn't really be happened, right? So if we were right in making this assumption, then large values of this are very unexpected. But they might be, large values of this might happen all the time if we are wrong in making this assumption. But given that we believe this, we don't really believe that this should realize to be a very large value. So this is evidence that our null hypothesis is not actually true. So we would go ahead and reject the null hypothesis, and in turn then we start believing that the alternative is true. Now that we've understood the intuition of the two-sided t-test, let me walk you through the details. To apply the two-sided t-test, we will need a decision rule. And a decision rule is a rule that for every sample tells us whether we should reject the null hypothesis or not reject the null hypothesis. So the decision rule for the two-sided t-test is based on a so-called test statistic. And statistic is just a fancy word for a number that you compute from the data, essentially. And our test statistic, for a test statistic, we build on our notion of basing the test on something that can be interpreted at estimating the distance from the null hypothesis. So we're looking at the difference between the estimated beta 1 and the hypothesized beta 1. Now, just using this difference turns out to be a little problematic. And the reason for that is that later on we will have to characterize the distribution of the test statistic under the null hypothesis. And when I say the distribution under the null hypothesis, then I mean the distribution assuming that the null hypothesis is true. And the problem that we encounter here is that we know if the null hypothesis is true, this has a normal distribution, right? But we don't know its variance. So if I want to draw the density for this normal distribution, I will know it's centered at 0, but I won't know the variance. So I don't know, should I draw a density that corresponds to the distribution with a very small variance, or should I draw a distribution that is very spread out and has a large variance? And the way to fix this is that we divide here by the standard error of beta hat 1. And then we know under the null hypothesis, this will have a standard normal distribution. And now, our decision rule will be compute the test statistic, and it would be nice to have a symbol for it. So let's call it t hat. Compute the test statistic, and then if the test statistic is too large, reject. Right, and so this from looking at it before we draw the sample, t hat obviously is a random variable, but we can evaluate it at any sample and then it will give us a number. So this is a recipe to compute for every sample that we might draw a number, right? So we compute this number, and if this number is too large, we reject. So what does too large mean? Well, let's just define some number C alpha, and then if t hat is larger than C alpha, we reject, but also we want to reject for negative values. So let's say if t hat realizes to be smaller than minus C alpha, then we will also reject. So let's write that down. So we reject if t hat is larger than C alpha or t hat is smaller than minus C alpha. And this is obviously equivalent to rejecting whenever the absolute value of t hat exceeds C alpha. And C alpha we'll call our critical value. Another way of describing this rejection rule is to say reject if t hat takes values in a certain set, and so that set would be the set that is combined of this shaded region. So we can put it together from the intervals minus infinity to minus C alpha and C alpha to infinity. And this set of values for which we reject is called the critical region, and I will denote it by capital C alpha. So to summarize, so this gives us a well-defined decision rule. So for every sample, we have a recipe for computing a number of that is then the realized value of our test statistic, and we can compare this value of the test statistic against a C alpha and determine whether we reject or not. And obviously, to apply this in practice, what we're still missing is the numerical value of C alpha. So we have to determine what value this number should be. And that's what we turn to next. The value of C alpha is calibrated in a way that makes sure that our test doesn't lead us to make statements about the population model that are systematically false. To be a little bit more precise about what that means, we have first have to think a little bit about how statistical testing works. So we have our null hypothesis, and it could either be true or it could be false. And we have our decision rule that for every sample tells us to reject the null hypothesis or to not reject. So this gives us a matrix of 4 possible scenarios. So if we reject, then we will learn that H0 is false, right? So then we will learn something about the population, and we will be in a position where we can make a statement about the population. Statement about population, and the statement will be H0 is false, or equivalently H1 is true. And this is basically what we want to show, right? So we're interested in scenarios where H0 is false, and in these scenarios you also want to have our test tell us that H0 is false. If we don't reject, then we don't learn anything, because we haven't been able to disprove the null hypothesis, and we will not make a statement about the population. Don't make a statement. So let's first talk about the scenarios where we reject. So if we reject and if H0 is false, that is the ideal scenario, right? We wanted, so for cases where H0 is false, we also wanted to learn that H0 is false. We wanted to make the statement H0 is false, and here we are able to do that. So that would just make us very happy. If we reject if H0 is actually true, then we will make the statement H0 is false, even though H0 is true. So we're making a statement that is false, right? We're making a wrong statement. So we're making a mistake. And this kind of mistake is called type 1 error. And this is basically where you don't want to end up. You don't want to end up making a statement and having the statement be false. And this is what will determine the value of C alpha. C alpha is chosen to make ending up in this scenario unlikely. So we calibrate C alpha basically so that the probability of us making a false statement is very small. So there are still 2 scenarios that I haven't explained, and while we're at it, I might as well talk a little bit about this. So let's look at this scenario first. Here H0 is false, so we want to make the statement H0 is false, but we end up not making a statement. So that obviously sort of is a little sad. But it's not really a mistake in a way sort of that we just refuse to make statements. So we'll just say, given sort of the evidence in the sample, we're just not convinced that the evidence doesn't convince us to say that H0 is false. It could still be false. We just don't have any conclusive evidence here. Huh? So we're not making a statement, and but by not making a statement, it's impossible for us to make a false statement, right? Still, it's a little unsatisfactory to end up here. And so whenever you end up here, so statisticians call this a type 2 error. And I find this very confusing because it seems to indicate, it suggests that this is an error in the same way as this is an error, but that's not true, right? Here you're saying something that is not true. Here you're just not saying anything at all in a scenario where you would like to say something, right? So these two types of errors are not similar at all. So what about the last scenario where H0 is true and you don't reject? So you're not making a statement, but also we're in the scenario where H0 is true and we really care only about scenarios where H0 is false. So here we end up not saying anything, but also there's nothing really for us to say, right? So if we wanted to find out that H0 is true, then we should have put it as the alternative hypothesis, right? So here, if we're interested in this scenario, we should reformulate our null hypothesis and use a different test, right? But if we have chosen our null hypothesis correctly so that it really reflects what we want to learn, then we just don't care what we do up here. We don't care about the scenario. It's okay not to say anything. So now let's look into choosing C alpha. So C alpha is chosen such that the probability of type 1 error is small. Let's say equal to alpha, where alpha is some small probability that is specified by the researcher who applies the test. So the researcher would say, I want the test to guarantee that the probability of type 1 error is at most alpha equal 5%, for example. So let's express this probability using symbolic notation. So it's the type 1 error is the probability of rejecting. And this probability is computed under the assumption that the null hypothesis is true. So to indicate that I'm computing this probability under the assumption that the null is true, I'll write assume that the null is true, or in other words, that beta 1 is equal to beta 1 not. So to compute this probability, I'll have to characterize the behavior of t hat under the assumption that the null is true. So we already know that if beta 1 equal beta 1 not, then t hat is well approximated by a standard normal distribution. So its distribution looks a little like so. And we reject whenever t hat is larger than C alpha, which happens with this probability, or smaller than minus C alpha, which happens with this probability. Now in computing the probability of type 1 error, we can exploit the symmetry of the standard normal density. So these two areas have to be the same. So we'll first compute this area, and then we know this area is the same. So what is the probability of ending up here? So what is the probability of t hat being larger than C alpha? It's just probability 1 minus the probability that t hat is smaller than C alpha. And now really have to decide what the C alpha should be. And it turns out that the good choice for C alpha is the 1 minus alpha half quantile of the normal distribution. Why is that? Well, let's plug that in. And this looks like something that you've seen before when in the revision for normal quantiles, except there you saw a z, but z was just any standard normally distributed random variable. So so like t hat and z would behave the same. And here I just put any probability p, but 1 minus alpha half is a probability, right, if alpha is small enough. So we can just use the result from before, right? And so we know by the definition of normal quantiles, this will be p, right? So let's plug that in. So 1 minus, so I copy that, and p in this case is 1 minus alpha half. So I'll have 1 minus 1 equals 0, minus minus turns into a plus, so alpha half. Right, so this area is alpha half. By symmetry, this area then is also alpha half. So the probability of rejecting, if the null is true, is given by alpha half plus alpha half equal to alpha. And so it's exactly the probability that we want it to be. And this is guaranteed by this choice for C alpha. We know everything we need to know to apply the two-sided t-test. Let's suppose that we want to test the null hypothesis beta 1 equal to 5. So we have chosen beta 1 naught to be equal to 5. Also, let's suppose that we are happy with a probability of type 1 error equal to 5%. So how do we test this hypothesis? That's right, we draw a random sample, and then on that random sample we compute the test statistic. Let's suppose that our estimate is given by 2.7 and we observe a standard error of 0.8. Now we can compute the test statistic, and the observed test statistic would be 2.7 minus 5 divided by 0.8. To compute this, we can use the calculator function in Stata. To enter the calculator function, we type display, or if we are lazy, and now since we're real Stata experts by now, we can just type di. So we type di and then we put in the expression that we want to compute, and we get minus 2.875. Next thing we have to do is we have to figure out what our critical value C alpha is. So we know generally C alpha is given by the 1 minus alpha half quantile of the standard normal distribution. If we plug in for alpha, then this is the 0.975 quantile. To figure out this quantile, we can use a computer. In particular, we can use Stata. Again, we enter calculator mode, and then we use the function inf norm and put the quantile that we want to compute, so 0.975, and we get a number that is approximately 0.96. Now we have to apply the decision rule. So our the absolute value of the observed test statistic is 2.875, and that's larger than 0.96, which is the critical value, that means we reject. So we will believe that H1 is true, or that beta 1 is unequal 5. Now going to look at one very common application of the two-sided t-test. The two-sided t-test allows us to test hypotheses of the form beta 1 equal to a number. For example, we could choose this number to be 0. Now beta 1 is the effect of x1 on the outcome. So if we say beta 1 is equal to 0, this is equivalent to saying that x1 has no effect. Suppose that we reject the null. Then we stop believing that there's no effect, and we will believe that there is an effect. So for example, if in our study time example, if x1 is study time, if we reject the null hypothesis that beta 1 is equal to 0, then we have shown that the amount, so how much you study, will have an impact on your exam score. In this case, we say x1 is significant if we don't reject h0, then we say x1 is insignificant. Let me briefly comment on this. First off, suppose that you've shown that x1 is significant. In our everyday speech, we use the word significant in a certain way, in particular, so we take it to mean that something is substantial, has a substantial impact. For example, if I tell you that x1, or how much you study in the exam for the exam, has a significant impact on your grade, then what you hear is that your choice of how much you study substantially impacts your grade. But this is not how we use the word significant here, right? Here it just means that we are able to distinguish the effect statistically from 0. So we are establishing the effect that the effect is not 0, it could still be very, very small. This is what the whole discussion about statistical significance versus economic significance is all about. So some people argue that we are never really interested in showing statistical significance, so establishing that the effect is not 0. What we are mostly interested in is also showing that the size of the effect matters and is economically meaningful. Second comment: suppose you have you don't reject the null hypothesis, so you show that x1 is insignificant. So as always, when you don't reject the null hypothesis, we don't actually learn anything, right? In particular, we don't learn that beta 1 is 0. Right? All that we learn is that we don't have enough data to conclude that the effect is not 0, right? Big difference.